Hello. In previous lectures, we have discussed the basic rules regarding designing of beam. Now here we will discuss the design steps of simply supported and cantilever single reinforced beam. So first of all, write down given data which is given in your numerical, and in second step calculate the trial depth. So we have here two formula to calculate the trial depth. First is the D equals to L divided by 20 into modification factor if simply supported beam is given, and second is D equals to L divided by 7 into modification factor for the cantilever beam is given. Now here we know that the modification factor is basically depend on the AST provided and AST required. So now here we don't have any AST, so for the calculation of modification factor, either assume percentage of steel 0.8% or directly assume the modification factor as a 1. Choice is yours. Now once you calculate the D, small d means effective depth, then assume the clear cover and the diameter of bar, and then calculate the overall depth, capital D. So formula to calculate the overall depth is small d plus clear cover plus 5/2 plus diameter of stirrups. Now here clear cover is assumed 20 mm. Okay, basically this clear cover is depend on the exposure conditions, and the exposure clear cover as per the exposure conditions is given in IS 456. You can refer the IS 456 to assume the clear cover. Now after that assume the phi means diameter of main bar from 16 to 20 mm. It is not necessary to assume the diameter from 16 to 20 mm. As per your requirement you can assume it, but it should be from 12 to 20 mm. Now after that you can assume the diameter for the stirrups from 6 to 8 mm, but now 6 mm is not used in market, so you can use the 8 mm for the stirrups diameter. Our second thumb rule formula for the overall depth is L by 12 or L by 15 for the simply supported beam, and D equals to L by 7 for the cantilever beam. Okay, once you calculate the overall depth, then next step is calculate the effective depth, width of beam. So we know that if width to depth ratio is near about 1.5 to 2, so approximately you can calculate here width D by 3 or D by 2 by using these two formulae. Or second, B equals to width of support. We know that the width of support is either wall or secondary beam. You can consider as a width of support is 230 mm. So by using these two formulae, first calculate width of beam and then consider the greater value for the width of beam. Once you calculate the width of beam, then check that width for the lateral stability, and this formula is given in clause 23.3 page number 39 of IS 456. So calculate L by using this 60B or 250B square by D formula, but whatever calculate this value of L should be less than of your given span of beam. Now once you calculate the dimensions, and if your width is saved, so go to the next step number 4, that is effective span. And the formula for effective span we already discussed in slab, and same formula is here to calculate the effective span. For simply supported, L equals to L plus D, and for second formula L equals to center distance between support. So consider whichever is small effective length for the simply supported beam, but if cantilever beam is given, so for that LE equals to L plus D by 2. Now after that, next step is to calculate load. So for load here we are considering 3 load. First load is the external load, that is W1, and W1 is equals to dead load of wall and the load transfer by slab. Now see here, Wn is totally depend on your weight of slab or total weight of slab transfer to the beam. If you are solving this numerical in exam point of view, so this W1 will be given to you in numerical but in practical you should calculate it properly by considering one way or two way slab. Now after that, calculate the self weight of beam W2 and formula is BD into rho. Next is the live load. If live load is given, then consider it, otherwise not necessary to consider the live load on beam. Generally live load comes on slab, not on beam. So if live load is given in numerical, then and then consider it, otherwise no need to consider the live load, because live load is considered in as an external load, so no need to consider live load. So after that, add these three loads and convert this load to the factor load by multiplying 1.5. So your WD is 1.5 into W. Now next, once you calculate the load, then go for the shear force and bending moment calculation. Shear force and bending moment calculation. So step number 6 is find MD and VD. So for simply supported beam, we know that the maximum bending moment formula is WL square by 8 and shear force is WL by 2. And for cantilever, maximum bending moment is WL square by 2 and shear force is WD into L. Once you calculate the factored bending moment and shear force, then next step is to calculate the check for depth. So check for depth is MD equals to MU limit, where MU limit is depend on grade of steel. Here formulas are given to calculate the MU limit. So we know that the Fe, if Fe 250 grade of steel is given, so for that formula is 0.148 FCK BT square. For Fe 415, 0.13 FCK BT square, and for Fe 500, 0.133 FCK BT square. So MD we have calculated in previous step, and MU limit is calculated as per the grade. Then from this formula, calculate the depth required for this bending moment, and whatever depth calculated from this formula, it should be less than of depth provided. So if this required depth is less than of your provided depth, then and then your provided depth is safe. Otherwise, you should be revise the depth and recalculate from the load calculation. After that, check reinforcement. Check reinforcement means what? Which reinforcement you should be provided for that particular beam, single reinforced section or double reinforced sections. So if your MD is less than MU limit, so we should design that particular beam as a single reinforced section, and if your MD means design or factored bending moment is greater than MU limit, so design your particular beam by considering the double reinforced section. While calculating MU limit, you should consider the depth, provided depth, to calculate the MU limit. Then after that, calculate main steel. So step number 9 is main steel. We know that the formula to calculate the main steel, that is 0.5 FCK Fy in bracket 1 minus under root 1 minus 4.6 MD divided by FCK BD square into BD. So calculate AST required as per this bending moment, and then check this AST required with the AST minimum. So in basic, we already discussed the formula for AST minimum and clause which is given in IS 456. So calculate AST minimum as per this formula and compare with this AST required. If AST minimum is less than AST provided, then and then your calculated AST is okay. Otherwise, you should consider this AST minimum as a main steel. Means if AST minimum is greater than AST calculated here, so consider AST minimum as a reinforcement for your main beam. Now once you calculate the AST, then go to calculate number of bars, and for calculating number of bars, first assume the diameter of bar, and diameter of bar should be from 16 to 32 mm as per your AST required, and then calculate small AST, where small AST is the area of one bar. Okay, and then calculate number of bar. So number of bar formula is AST provided divided by small AST, means area of one bar. And if you are considering the round of bar, means suppose your number of bars, calculated number of bars is 2.5, so 2.5 bars we are not providing in practical point of view, so we are providing, or you will round up it 2.5 to 3, so your area of provided steel will be increased. So calculate that area of steel, okay, provided area of steel, and then go for the check for deflection. So step number 10 is check for deflection. So we know that the formula to calculate the check for deflection is L by D max is greater than L by D provided, where L by D max is as per the deflection control, which is given in IS 456 page number 37. So as per that, our formula is 20 into modification factor for simply supported beam and 7 into modification factor for cantilever beam. Now here modification factor is calculated as per the IS, which is given in figure 4 IS 456. So for that condition, we should calculate the modification factor, and if L by D max should be greater than of L by D provided, then and then your beam is safe for the deflection. And if this check is not satisfied, so in that case you should revise the dimensions, means depth, and recalculate or redesign your beam from second step. Now if your deflection check is satisfied, then go to the next step, that is shear reinforcement. And for shear reinforcement, first calculate the nominal shear stress, that is tau v, and formula for tau v is Vd divided by Bd, which is given in IS 456 on page number 72. After that, calculate design shear stress, and formula for design shear stress is tau c. The formula as well as the table required to calculate the tau c is given on page number 73. Table number 19 of IS 456, you can refer to calculate the value of tau c. Now after that, calculate maximum shear stress, and maximum shear stress is calculated as per the table 20 of IS 456, and then compare the tau v, tau c and tau c max, means nominal shear stress, nominal shear stress, then design shear stress, and the maximum shear stress. So in comparison, if tau v is less than tau c is less than tau c max, then shear reinforcement is not required. Basically tau v and tau c is important. If your tau v is less than tau c, then shear reinforcement is not required, but provide the minimum shear reinforcement, that is 8 mm phi 2 leg stirrups about 300 mm center to center. But if your tau v is greater than tau c, then shear reinforcement is provided, and if shear reinforcement is required, then use following steps, means point number 4, that is shear to be carried by reinforcement. So for providing the shear reinforcement, first we should calculate the shear carried by reinforcement, and the formula to calculate the shear carried by reinforcement is VUS is equals to VD minus tau c BD. So for the calculation of shear reinforcement, first we should assume the stirrups and assume 8 mm phi 2 leg stirrups, and find the ASV, where ASV is the ASV is the area of stirrups. Now once you calculate the area of stirrups, then go to the calculation of spacing of stirrups, and the spacing of stirrups should be minimum from these four formula. SV equals to 0.87 Fy ASVD divided by Vs. Second formula is SV equals to 0.87 Fy ASV divided by 0.4 B, and next is SV equals to 0.75 D and 300. So provide the spacing whichever is small or less from these four SVs. Now after that, write the sentence, that is provide 8 mm phi 2 leg stirrups above spacing which is the less than from these four values. Okay. Also provide 2 bars on top corners of 10 to 12 mm in compression zone to hold the stirrups. Okay. Now after that, check for development length, then calculate the actual LD and then permissible LD. So formula for actual LD is sigma S phi divided by 4 tau BD, and permissible LD is 1.3 M1 VD plus L0. So how to calculate this M1 VD, sigma S and tau BD we already discussed in design of slab. Okay. So and last step is to draw the reinforcement detail as per the main reinforcement and the stirrups. Thank you.